Today we will discuss some other design issues related to the operation amplifier. So, as an example, today I will take how to design a temperature indicator. So, we take temperature indicator design we do. Now, for this we have to first select a temperature sensor. So, we have various sensors are there. I will see about them little later. Today we take, for example, IC sensors. So, we have IC sensors are available in the market. Using that, how to design a temperature indicator. For example, IC sensor, your classical sensor is LM335. This is available. This is a temperature sensor, and it is used extensively in the industry. This is an older version of this. The new version of this also, the LM35 is there. Let us see how to use this LM335 and then operation amplifier and other components, so that we can design a temperature indicator. Now, this LM335 is basically a transistor based temperature sensor, because we know if we take a transistor, then if you look at the base emitter voltage, for example, we know that between base and emitter, when it is forward bias, we have around 0.6 volt. This forward bias voltage changes with temperature. We know the temperature coefficient of that is minus 2.2 millivolt per degree C. Actually, that means when for every 1 degree temperature rise, you will have voltage drop of 2.2 millivolt per degree C. In the sense, if at 25 degree C, for example, if at 25 degree C, if the VBE is VBE at 25 degree C, VBE is equal to 0.6 volt, then I'd say at 35 degree C, so 10 degree above, the VBE, for example, will come down 10 into 2.22 millivolt. That actually means that is you will have 0.5 22 millivolt comes 0.578 volt. It comes, that is 22 millivolt are decreased for 10 degree temperature rise. So, using this transistor base emitter voltage change as a basic element, that they developed this IC sensor LM335, and LM335 today available for us to use in this form. Like, for example, if you look at LM335, the symbol is given is like a Zener diode. So, actually there is a third terminal associated with this. Let us not worry about that at this point of time. So, this symbol is like this. Now, to use it as a temperature sensor, now what I do is I have to pass a current through this. That current should be minimum of 1 milliampere. So, how will I pass the current? So, I connect on resistance, then connect, for example, to a plus 15 volt supply. Then I select this resistance R, this resistance R, such that the current that is flowing through this is 1 milliampere. So, we have to make sure that 1 milliampere current all the time it flows through that. Then only then the sensor works properly. At the same time, we also should not send more than 10 milliampere current through this. You can pass the 5 milliampere current, but then that there will be a heating up in this, and that will give a temperature measurement error. So, to avoid that, we try to operate at the least possible current, that is 1 milliampere. So, I have to have 1 milliampere current minimum flowing. More than 1 milliampere, up to 10 milliampere, there is no problem, it works all right, except for the small temperature error. So, what is the value of R I have to select? That is the first question that we have to look into that. Now, this sensor can be used actually up to 125 degree C. Now, even if I take it as for our application, let us assume we want up to 100 degree C. So, temperature range is actually up to 100 degree C. Assume for our design we have to display temperature of 100 degree C. Now, if it is 100 degree C, then at 100 degree C, what is the voltage at this point? then assume that our other temperature range is T high is 100 and the lowest value is assume we want to go up to 0 degree C. That means I should look at this point, what is the voltage I will get at 0 degree C, what is the voltage I will get at 100 degree C. Now, if you look at the data sheet of this LM335, it says that it gives a voltage across this xenon, that is voltage across this voltage across this is 10 millivolt per degree K, that is for example at 0 degree C, voltage across the sensor will be 2.73 volt. Then at 100 degree C, voltage across the sensor will be 3.73 volt, because 0 degree corresponds to 273 degree K. So, basically the V output of sensor is actually 273 plus temperature in C into 10 millivolt. That is what the temperature gives. That is why at 100 degree C we will get 3.73 volt. At 0 degree C it gives you 2.73 volt at 0 degree C. At for example 1 degree C, then you will get 2.74 volt, and at 2 degree C you will get 2.75 volt, like that. For every 1 degree 10 millivolt increase in voltage you will see across the sensor. So, if I want to measure the temperature, then I should keep the sensor wherever I want to measure, and then I will get a voltage like this. Say at room temperature, for example 25 degree C, I will get 2.73 plus 0.25 volts, that will give me 2.98 volt. So, we will get to, but only problem is if I want to use as a temperature indicator, then it is good if I get at 0 degree C 0 volt, at 100 degree C 1 volt. That would be good, because I can connect the meter directly and then the display will show me the actual temperature. One need not worry about this 2.73 volt. So, the actual is at 0 degree C it is giving 2.73 volt, but this I had to convert into 0 volt. At 100 degree C it gives me 3.73 volt, that I convert into 1 volt. So, essentially if I look at the thing, what I require is from the instrument, that is the sensor, I will connect to my circuit, and my circuit should give at 0 degree C 0 volt, at 100 degree C it should give me 1 volt. So, at any other temperature, for example 50 degree C, obviously it will give me 0.5 volt. So, one can connect the display and then directly see the temperature, that is our aim. So, how to achieve this? So, what I do is I will use the operation amplifier, and then I can do this job in a simpler way. Say I take the operation amplifier. I know the operation amplifier, we can use it as a non-inverting amplifier. In that case I will give a voltage here, and then I give the resistance here. This you have already studied in your earlier class. So, you know that this is RF and R1, then V input is this and that V output is here, then V output is given by V input into 1 plus RF by R1. This you may be familiar from your earlier circuits. So, I will not get into the derivation of this. One can easily do this work. You have already done this in your undergraduate course. Now, or if you are using it as a non-inverting amplifier, then I can show that the circuit looks like this. That is, I can put the same thing. I give a input here, ground this, and then give the input at this point. Then connect the feedback resistance. then you have RF and R1 and Vn, then you will get V0 as minus Vn into Rf by R1. So, this also you have studied. Now, we also know operational amplifier can be used as a summing amplifier or to subtract the voltages. So, in this application, first what we will do is we will use a non-inverting amplifier and then try to get this one. So, what I will do is I will take the sensor first. So, I have to bias the sensor. So, I put the plus 15 volt, then I want to make sure 1 milliampere current is going through this. I know at 100 degree C this point will be 3.73 volt, at 0 degree C it is 2.73. So, in the worst case at 100 degree C I will have 3.73 and then that makes voltage across this resistor will be 15 minus 3.73 volt. That is the worst case voltage that will be seen across this resistance, and that works out to be if you calculate that you will get 3.73 volt. So, you will get 11.27, that is 11.27 volt you will get across this resistance. I want to make sure 1 milliampere current minimum. In this example, let me take 2 milliampere because it can work from 1 milliampere to 10 milliampere. I will come back to this why I have taken 2 milliampere. So, if I want to pass 2 milliampere current through this, then the voltage across this resistance is now in the worst case will be 11.2 volt. So, with 11.2 volt if I want 2 milliampere current through that, then the resistance value R will be that 11.27 volt divided by this current, that actually turns out to be 11.27 volt divided by 2 milliampere current I take. That if you convert into resistance, then it becomes 5 then you will have 5.6 K resistance you will get. If you do this division, you will get 5.6 K. Now, if I look at the nearest value that I can put 5.6 K resistance. So, if I put 5.6 K resistance, then I know approximately 2 milliampere current is maintained through the sensor. So, I will put here 5.6 K. Now, if I see the voltage at this point, that will give me temperature actually. So, if it is at 100 degrees I will get 3.73 and then at 25 degrees I will get 2.98 volt across this. So, our voltage at this point with respect to ground. So, I will say simply voltage at this point. Only thing is at 0 degree C it is giving 2.73 volt, that I have to make it 0 degree using in the operation amplifier. So, that I can do it in the following way. So, what I can do is now I will put the sensor, connect this, then I put this 5.6 K, connect this to plus 15 volt, then I take the operational amplifier, this plus, grounded, I got minus, so I can do this. This is simple inverting amplifier. Assume I have put equal resistances here, say 100 K and 100 K. Now, I have put the equal resistance. So, essentially at 0 degree C, at this point I will get 2.73 volt, then at this point that V0, that will give me minus 2.73 volt, assuming there are no other errors in the operation amplifier. This is simply a inverting amplifier. So, basically the plus had become minus. You may wonder that why did I select 100 K, I would have selected even 10 K, I would have selected 1 K. Remember that if I this current whatever that is going through this is 2 milliampere. Now, if I put a resistance here and I know that this is 0, So, this point also have to be 0. This is the essence of the operation amplifier working that we had discussed earlier. So, this input and this point are essentially same. So, if this is 0, ideally this is also 0. So, the current that is flowing through this resistance is 2.73 volt divided by this resistance. So, this current basically comes from here and then part is going here, part is going here. So, this current should be small. If this current is large, then current flowing through this will come down, and if it happen to come below 1 milliampere, then temperature indication will go wrong. That is why we have selected here 100K. Of course, we can go very high value. If we go for high value here and high value here, we will have error associated with the operation amplifier, that we will see little later. That is because of the bias current, you may get large error. That's why we don't want to put more than 100K also. Larger value also gives more problem. But smaller value if I put, that gives problem because most of the current will go through this and less current will go here. So, you either want to select a low value, because at this point if I take 2.73 divided by 100K, it comes roughly about 27 microampere current, and having 2 milliampere coming here, 27 microampere going is no issue at all. Still it has enough current to say that current is 1 milliampere. So, 100K is perfectly alright here. But then our original aim was that V0 should be 0 volt when the temperature is 0 degrees. Suppose if they keep this one in ice, then this will give me 2.73, but I want here 0 volt. So that I can connect a meter here, display here, and the display will show me the actual temperature. That is our aim. So, I put a display and the display will show me say like this. If like this, if it shows, I am happy. So, for that I give a 0 volt. That means if I want I had to remove minus 2.73 how to remove. So, I can do one thing, I can subtract, I can add this operation amplifier can be used as a summing amplifier as well. So, I can give a voltage here, for example, I can give minus voltage here. This voltage can be minus 2.73 volt. Now, if I give minus 2.73, if I put here 100K, then you will find that this V0 now actually tend to 0 volt. This is because now you have two sources, one is this, you got V1, another is V2. So, how to find the net output voltage? So, we have to take one at a time. So, first we take V1, then effect of V1 with V2 grounded. So, I will take assume that this is grounded. So, I remove this guy, then put this to ground. Now, what is the output voltage that I will get here? For example, what is the voltage I will get here? I find out the voltage due to V1, what is the effect at V0. Then I ground V1 and give V2, find out what is the effect. I add both, that will give me the net voltage at the output. So, already those are familiar. This is maybe in inner struggle so much, you can say that the two voltages here, this is V2 and the other one is V1. The net output is V1 and the gain is 1. So, V1 is anyway inverted. So, output will be minus V1 and V2 again the gain is 1 and that is again inverted. So, I will have plus V2. So, if V1 V2 are equal, then output will tend to 0. So, to make output 0, all that I have to do is I have to make V2 that is equal to minus 2.73 volt. So, I give here 2.73 volt, then this will become 0 at 0 degree C. Then if the temperature goes up, this will go to if temperature goes up, this will go to 3.73 at this point, say 100 degree C, then this will go to 3.73. This remains 2.73. That means if we see the output due to V1, that will be at this point at 100 degree C by C, at 100 degree C, then what is the condition that we get? at 100 degree C, then sensor will be 3.73 volt. So V output will be minus 3.73, then plus 2.73 due to the V2. So this is due to V1, this is due to V2, and the net output voltage is minus 1 volt. So 100 degree C it will show minus 1 volt. Right now we need not worry about this minus sign, but it serves the purpose. That is at 0 degree C now it will give me at 0 degree C it will give me 0 volt. At 100 degree C it will give me minus 1 volt. So if I connect the meter, then it will show correctly. But then there is one issue. Now if I go back to the earlier circuit, I will go back here. We have achieved this, at 0 degree C 0 volt by connecting minus 2.73 volt at this point. But then this voltage must be stable. If this changes, then output temperature also will output voltage also will change, and that give a erroneous reading. So we had to connect here a voltage source which is obviously stable, and it is to be 2.73 volt. If it is a stable voltage source, we have to connect a Zener diode only. So if I have a Zener diode of 2.73 volt, then the issue is very simple. Then I can connect the Zener and then the work is done. But unfortunately, in reality you do not get Zener of minus 2.73 volt. You have, for example, very good Zeners available, voltage of 1.2 volt, 2.5 volt Zeners available, 5 volt Zeners available. Now I am not talking of the regular junction Zeners, I am talking of low drift Zeners with temperature. Even though we are not putting this Zener inside the oven where we are measuring the temperature, but with ambient temperature this voltage should not change. So we have to have a stable Zener. The stable Zener you can get it in the band cap Zeners are very stable. For example, we have a Zener, the band cap Zener, say the classical one is LM336 for example, that gives you 30 ppm stability against temperature. So we have to use only 2.5 volt. This is available in 2.5 and 5 volt varieties. So they will give a very stable voltage against temperature. With the temperature, the voltage of the Zener changes only 30 parts per million. So there that we will see, even that is sometimes objectionable. But in this example we will take, assume we use a LM336 Zener to generate V2. Only issue would be it is not 2.5 volt, that what the Zener that we have is only 2.5 volt. So what happens if I connect that Zener, because I have no other go, I have to use only that 2.5 volt Zener. So if I take 2.5 volt Zener, then with that how will I design the circuit? So what I can do would be I can take our temperature sensor. We had 5.6 K here, and this is LM335, that is sensor. Then I take the output, then I connect to the operation amplifier, then I put 100 K here, then 100 K here, and that is the output. Now I put one more Zener diode. That Zener diode also to be biased, and that has to be minus, because that depends on how we connect it. For example, I put minus 15 here. Then if I look at this, it gives me 2.5 volt, say LM336. The symbol looks like both Zener, but this is temperature sensor. This is not Zener. This is a temperature sensor. Unfortunately, in industry, they follow the same symbol, and the manufacturer also give you the Zener symbol only for the temperature sensor. So we have to accept it and use it. So nevertheless, this is a temperature sensor, this is a Zener. This voltage, voltage at this point changes with temperature, whereas here the voltage at this point will not change much, it will be very, very small, that is 30 ppm. That is what we wanted. We want a stable voltage at this point, we want a variable voltage with respect to temperature at this point. So if I take LM335, then this will give me at this point 2.5 volt. So I can do one thing, I can connect this 100 K and connect to this, then at 0 degree C, this is kept at 0 degree C, then I will get here plus 2.73 volt, and at that time it is minus 2.5 volt. Then I will get output, the difference between these two, that will be minus 2.73, and this gives you plus 2.5. So the net result will be minus 0.23 volt. That is, instead of getting 0, we are getting 0.23 volt at 0 degree C. That is because we could not get because 2.73 volts ZNR is not available in the market. That is why this problem happened. Now there is one way of solving this issue. Now if I want, my aim is I want to make output 0 when this is when the sensor is kept at 0 degree C. Now one thing I can do, since it is only 2.73 volt, I need not keep 100K. For example, this 2.5 volt should produce this minus 2.5 volt should produce here plus 2.73 volt to cancel out this 2.73 volt given by this. So what I can do is I keep this 2.5 volt, change this resistance such that this and this put together gives gain little more than 1. So that this 2.5 itself able to give 2.73 at the output. So if I look at this route, then I had reduced this resistance from 100K. So how much I had reduced? This what is required is that I had to have the voltage of this 2.5 into this RF. I take this I take R1 into RF by R1 should give me 2.73. Now if I take this RF as 100K, then this comes 2.5 into 100K divided by R1 will get to give me 2.73 volt. Now if I see this one, then what is the R1 comes? So you will have 2.5 into 100K divided by 2.73, that is the value of R1. So you will find that the R1 will be little less than 100K, because this is little less than 1. So that means you will have this 100K little less than 100K, maybe 82 kV at calculate and see. So once if I put this value of R1 here, not 100K, then I will get at 0 degree C this is 2.73, and then at 0 this is 2.73, and this will be 0. At that time this is fixed at minus 2.5 volt. So I have to put this value of this value of R1 here. So this, if you work out, it may come to this thing. So you don't find even that value readily available. So normally what is done is we will put, this will be around 82K. So what I will do is I will put on one more additional resistance here, and here for example I put 82K and a very small resistance here, variable resistance, and then that actually should cover this range. For example, this may come something like 91K, 92K. So if it is 82K, then this has to be adjustable to 10K. Maybe I can put 22K pot here. So I can adjust this to get 0. So normally what is done is you keep this one at ice, and then this gives you 2.73. Adjust this to get 0 degree here, so that at 0 degree C it gives you 0 volt. So that is how the 0 adjustment is done. So you can adjust this potentiometer. Say I will call this as P1, and of course this resistance is R1 here. So you have this resistance we call R1, 82K, and this is P1. So adjusting P1, we can calibrate this instrument, that is keep this one at ice and adjust P1 to get 0 volt at this point, that represents 0 degree C. Now the problem is not yet fully solved, because we know that the sensor also has error. Some 0 degree C it may not give exactly 2.73, it may give a little less or more. And if you see the data sheet, if you are not adjusting, they are given on third terminal, if you are not using and adjusting, this can have a error. So at 0 degree C, if it is not giving 2.73, if it gives 2.74 or 2.72, it is not a serious problem. I can adjust this and get it 0. That is the reason I had put in fact a potentiometer. So even that means we can calibrate out even whatever error is there on the Zener. So that is why the potentiometer is required here to do it. Similarly, the other problem comes that when temperature goes to 100 degree C, suppose if this goes to 100 degree C, then you may not get 3.73 exactly. It can have a error. Suppose it goes only 3.72. Then 100 degree C, I will not get 1 volt, I will get only 0.99 volt, because the difference the 10 millivolt will be lost here, because this is having gain 1. So whatever change is taking place going to take place as it is with only inversion, the polarity inversion. So the problem comes that if this is not going exactly 3.73, then there is nothing to adjust. So it is essential that when I put it in ice, even though this is not going 3.73, I have to make it this to go to 1 volt. So then only our instrument will be correct. So what I do is, if this is going less or more, then I should be able to adjust. Some of the sensor may go even more than 3.73, may go to 3.74 at 100 degree C. So I should able to adjust when the voltage is less or more. So that I can do by adding gain resistance, by varying the gain here. Because if it's not 3.73, only 3.72, all that I need to do is I had to go more than 100k, because if both are 100k, gain is 1. If it goes little more than 100k, then the gain will be little more than 1, then 2.73 will be amplified by little more than 1. So if it goes only 3.72, then if I have a gain little more than 1, that means what I need is 3.72 into the gain whatever I have, that should give me 3.73. So the gain will be obviously little more than 1. So similarly, if the voltage goes more, for example it goes to 3.74 at 100 degree C, then I add 3.74 into gain should give me 3.73 at the output. So the gain must be variable more than 1, as well as if necessary we have to bring down less than 1. So that I can achieve by changing this feedback path. So what I do is, I will add the resistance here, then I add the one more potentiometer here. So this I keep it as a potentiometer like this, and this is a fixed resistance. So I call this is P2 and this resistance is R2. So at any given time, the combination of P2 plus R2 should give me the gain. So if it is 100k, if you want 100k gain, then 100k with one gain, then R2 plus P2 should be 100k. If you want more than one gain, in that case P2 plus R2 should give me more than 100k. If less than 100k, then P2 plus R2 should give me less than 100k. If less than one gain, then this combination should give me less than 100k. So normally what is done is, I will keep this one somewhat because the variation here is not going to be very high. Normally within 1 or 2 degree only you will get the sensors. So I can keep this one 82k, and then I put here for example 22k. That will give me maximum of 104. If I want, I can also increase the value, so that it is easily adjustable. Okay, what I do is, I will put the I take P2 little higher so that my adjustability is better. So I can put, for example, P2 as 47K, and then this is fixed 82K. So I can adjust now 129K at one side when the potentiometer is maximum. The potentiometer goes down, I will have 82K. So now what I do is I will put this one at 100 degree C and adjust P2 to get 1 volt. Then I keep this at 0 degree C ice, then adjust this P1 to get 0 degree C. So like that I should repeatedly do 3-4 times. That is, first I keep it at ice, adjust P1 to get 0, then keep it at 100 degree C, then adjust P2 to get 1 volt. So that means that you have to iteratively do 3-4 times, because when you are adjusting P2, in fact this can also get altered. So it is essential that you have to go back and readjust at 0 degree C at P1. So you have to adjust iteratively P1 and P2 a few times to get the correct value. So essentially what we do is, we will first the step, calibration step would be keep the sensor in ice. Adjust P1 to get P0 is equal to 0, then keep the sensor at 100 degree C, adjust P2 to get output as 1 volt. Then repeat step 1 and 2 several times. That is how it is calibrated. Once it is done, then we can use this for temperature measurement. Once that it is calibrated, then if you put it at 50 degree C, they will give you if you put it at 50 degree C, then you will get 0.5 volt. If you keep it at room temperature, then you will get 0.25 volt. This is how the operation amplifier is used here for temperature measurement. I have taken this example to illustrate how can use the operation amplifier for summing application. Here actually we are summing two voltages, this V1 and V2 are summed. Of course we are reverse summing, and then you are getting the voltage here, and the individual gains also can be varied by varying this, because this voltage is this is producing output corresponding to the ratio between this and this. This voltage is producing output corresponding to ratio between this and this. So not necessarily that both at all three have to be equal. So to illustrate this example only, I had taken this LM335 and had shown you how to make a temperature indicator and how to calibrate, how to make a real world equipment. What is the situation that existing. For example, the sensor may not be exactly giving you 10 millivolt per degree C, or it may not be 0 degree C, exactly may not be giving you 2.73 volt. All that considerations, with all that limitations, you can get the required output. This is essential in electronic circuit design. Of course, we have not done one more work, that is what is the value of this this resistance. We have not fixed the value for this resistance. This is not very difficult. This is similar to what we have done here. This is also Zener only. This is Zener. So this is 2.5 volt and this is 15. So you have a 12.5 volt across this. And here also it needs 1 milliampere current through this, and some small current is flowing through this. Even if I neglect that, if I want to keep the same 2 milliampere current like what we have done here, 2 milliampere current through this, because this also works well from 1 milliampere to 10 milliampere. So if I want 2 milliampere current to flow through this, then 12 volt is across, 12.5 is across this. So 12.5 divided by 2 milliampere gives me 6.2 K, that I can use very well 5.6 K resistance here, which will give me little more than 2 milliampere, because this success up to 10 milliampere. So no issue, I can put 5.6 K. So that will give you about 2 milliampere and then very small current 2 microampere only flows through this, because this is this point is 0. So this is 2.5. So 2.582K is only very small current that will still maintain 1 milliampere current through this. So no issue, I can put this 5.6K. That completes the complete circuit design for temperature indicator. Of course, the output is minus. For example, even it is 100 degree C, this is going plus 3.73, that will come as minus 1 volt here. If I want output to be plus, then I have to do one thing, I have to reverse these ZNRs, that is all. Then the same thing works all right. For example, I can do that by reversing this. Minus is not an issue, one can retain the same circuit. Nevertheless, one can do this. It won't take much time. So we can put the minus supply here, and then we put the sensor, reverse it. So that gives you LM335 sensor. Now you will get here minus voltage, that will become plus when I connect this. Then for the reference ZNR 2.5 volt, I will put plus, because when this is minus, this must be plus, then only it will take care of that. So I can have this 100K, and that is P2, and you have 82K, and this is P1, and this is 82K, and this is that 5.6K, and then this is also around 5.6K. So that makes output go positive when the temperature goes up, because when the temperature goes up, this voltage will go up. So that minus going up will make the plus to go up at this point. So V0 becomes plus now. So this also can be done to give positive voltage. Now all that need to be done is you connect the meter here, and that will show 0 degree C 0, 100 degree C it will show 100. And that can be achieved. For example, I can connect a voltmeter of 1 volt to full scale. Then when 1 volt comes, it definitely will show this. All that need is I put on a dot, and that comes as a display. Now in this case we have just taken a design example, and then we are done using the summing property of the operation amplifier. Of course, there are several issues are there still. We may ask how accurate is this sensor. You know, you are calibrate. Once you calibrate, you know, the instrument will, this will give you 0 degree C 0 volt, 100 degree C 100 volt. But then when temperature, room temperature changes, not the temperature of this, assume this temperature is fixed, it is not changing, but the room temperature assume it is changing. That is, then all these components which are in the room, they all will change. If they change, like for example, the operation amplifier temperature changes, then its property changes. That produces a different output voltage. Similarly, the resistance value may change with temperature, and this may resistance may change, and this resistance may change with temperature. This also will change with temperature. This also will change. All these things will make it. This is not accurate, because this may give accurately 3.73 volt at 100 degree C, but this chap may not give all the time 100 degree C equal to 1 volt. At room temperature it may give 1 volt. At high temperature this may not give 1 volt, it may go higher or lower depending upon the components, that how these components are drifting and how the operation amplifier parameters are drifting. And that is the error budgeting, because error budgeting is very important in the analog circuit. Just by designing this circuit is not much use, because if these components drift quite a lot, and then if at 100 degree C the instead of going 100, if it goes 120, then you have a 20 degree error, and that will ruin the entire design. So one should aware what is that in store for us when we are using this, or when for that matter when you use any analog circuit, how the components values will change, or how the operation amplifier behaves, and how that thing will affect the output voltage. This is to be considered and it should be looked into that from the beginning. Now, if I look at the resistors here, now do they change with temperature? For example, I have a 100K, I take for example 100K, that resistance value is 100K, sorry 100K at 25 degrees C. Then I look at 100 degrees C, or for example the room temperature, if we take initially for example only room temperature, the room temperature goes at say 50 degrees C. Then the question is, what will be the value of this resistance? There is if it is 100K at 25 degrees C, then at 50 degrees C, what is the value of that 100K resistance? Will it be higher or it will be lower? And if it is higher or lower, how much it is going to change? And we know that for example in this case, if the for example this 82K we have used, this 82K, if the if the temperature goes up, if this goes to 85K, then we know at 2.7 at room temp at 100 degrees C of this, you are not going to get 1 volt, we are going to get more than 1 volt, and that will be read as error. So it is very important to know how this value of resistance changes with temperature, how this changes, how this changes, how this and how this changes. And considering all that only, I can reliably use this circuit. So one must know the error budgeting. Similarly, for example, we are using the Zener diode here, which is supposed to give me 2.5 volt all the time. But then I know that this is not going to be 2.5, because considering this voltage is 2.5 only, we adjusted P1 and then P2 to get the correct calibrated output. But what happens when temperature changes, the voltage given by the Zener also changes, because you should not assume that it is 2.5 means all the time it is 2.5. Zener is supposed to give that 2.5 volt all the time, but then it also has a error. For example, if I take this our classical sensor LM336, the manufacturer says the Zener drifts with temperature by 30 ppm. If you look at the data sheet of LM336, then LM336 says temperature drift is equal to 30 ppm per degree C. That is the voltage at this voltage at this point, what is available voltage at this point, what is there will be changing by 30 ppm per degree C. They are not telling whether it will increase or decrease. If you look at the data sheet carefully, they are telling it is plus or minus 30 ppm. That means some sensors that the voltage may increase with temperature, so for the same LM336 some other piece it may decrease with temperature. So you do not know which the sensor that LM336 with that particular piece what you have used, whether it has a positive temperature or negative temperature coefficient. Positive temperature coefficient it will increase with temperature, negative temperature coefficient means it will decrease with the temperature. Now that is not known, and also you have to see one more this spec the temperature drift is not telling plus or minus 30 ppm per degree C, he says plus or minus 30 ppm per degree C maximum, because he is not telling this temperature, the temperature with temperature the voltage at this point will exactly increase or decrease by 30 ppm. In one sensor there may not be any drift at all. In one sensor it can be plus 10 ppm, in another piece it can be minus 20 ppm, in third piece it can be plus 5 ppm, fourth piece may not have any drift at all. So we have to find only the worst case drift. With that, what is the error that you are going to get? Now consider only this LM336, and with that only, if this alone is drifting, what is the expected temperature error at the output? Let us calculate this today. Now so this is given as plus or minus 30 ppm per degree C. Now we have to find for what is the working temperature range. So we have to decide on what is the working temperature range. In the sense this temperature indicator will be kept in a room or wherever it is going to be used, and then we will have the sensor that is this, and this sensor of course will be kept in oven or wherever temperature to be measured, there it will be kept. But all these components will be kept inside the instrument, and the instrument will be kept very close to probably the sensor where it is measuring the temperature, but not at the same point. So this component, this zener, obviously will be in the room temperature. But then what is the room temperature? You know, room temperature morning, for example, if you look in the laboratory environment, morning in some places it can go as low as 0 degree C, and in some other place in the room it may go up to 45 or 50 degree in the noon, particularly in the summer. For example, if they are using this to measure a temperature in the process chemical industry. Now in the process chemical industry, the instruments are kept straight in the open field where sunlight directly falls on that, and also in some cases when the instrument is kept in the open, in cold countries even ice would be sitting over the instrument. So obviously for industrial, if I am using it for industrial measurement or for industrial grade equipment, then I have to assume that temperature of this changes from minus 20 degree to plus 80 degree, because even you know at noon, if the instrument is mounted in the open field, and if you go and touch the instrument in the instrument at noon, that instrument will be very hot. So you have to take it as industrial grade working environment up to 80 degree. So assume that this is for industrial grade equipment, that on worst case it can be minus 20 degree, at the other end, you know, at low temperature it can go minus 20 degree, at high temperature it can go to plus 80 degree. That means up to 100 degree temperature variation of this is possible. I am not talking about temperature measurement, I am talking of the instrument is used. So we know that this changes by 30 ppm maximum. That means 100 degree if I take, that will be a 3000 ppm change in voltage is possible for the worst case minus 22 plus 100 degree temperature change. So then what will be the voltage change here? Then what will be the voltage change that is expected at the output? So considering the industrial grade equipment, then temperature change I take it as 100 degree temperature change, ambient temperature change. This is for industrial grade equipment. So the drift of the sensor is temperature drift. Drift is 30 ppm maximum per degree C. So total drift will be (30 into 100) ppm, that will be equal to 30 into 100. So ppm means 10 power 6, 1 in 10 power 6. That many parts it can change, but the original voltage is 2.5. So original voltage is 2.5 volt. It's 2.5. So 2.5 for 2.5 volt, what will be the change? So I will see total change for 2.5 volt. For 100 degree, delta T is equal to 100 degree C. That is actually given by this 2.5 into 30 ppm and the temperature of 100, and per ppm I put 10 power 6. That is the expected voltage change for 100 degree temperature change. That actually works out to be 2.5 into 3 into 10 power 3 divided by 10 power 6. That will be 7.5 into 10 power minus 3, that is equal to 7.5 millivolt. That means the zener temperature will change in this case. You know, if we take this, the temperature, when room temperature changes, voltage at this point will change by 7.5 millivolt, because that means 7.5 millivolt change will produce roughly, because we had seen this and this produce gain. So, if this changes by 7.5 millivolt, this and this more or less equal to 1. So, we will have output 7.5 into 1, that will be 7.5 millivolt change at this point. That will give here at this point 10 millivolt is 1 degree, because 0 degree is 0 volt, 1 volt is 100 degree C, that means every degree 10 millivolt change at occur. Now, if here if we change 7.5 millivolt, output also will change by 7.5 millivolt due to the temperature variation of this. So, output will have a error of 0.75 degree, because 7.5 millivolt corresponds to 0.75 degree error. So, the Zener drift alone contributes for 0.75 degree temperature error in this example. Here we assumed this and this ratio 1. If the ratio is different, say 1.1, then I have to multiply in 7.5 into 1.1 and put it here, but we have taken it is in fact close to 1. So, you may have 0.75 degree error. This can be plus or minus. For example, if this temperature drift is plus, then it will go reducing. If it is minus, it will be increasing. So, we will say that my temperature measurement can be accurate only to 0.75 degree, plus or minus 0.75 degree, if I consider the drift due to this Zener alone. We assume there is no other drift in this case. Even with this alone changes, it can have uncertainty of 0.75 degree in this instrument. So, we have to see all other errors in the next session, because it is essential when we are designing instrument, what is the total error that is expected.